Chapter 5, Section 4, Factoring Perfect Square Trinomials and Differences of Squares. Um, Really what we've gone through in the first three sections of this, really last two sections are kind of the tougher ways to factor. You have to do it that way. And they're going to start talking about some patterns. They're kind of harder to recognize sometimes, but definitely not with difference of squares. I think that we'll talk about this probably in this next part of the video, but we want to recognize patterns. So we went through with this grouping thing so you can use some tools to form a pattern so you can make a factoring by grouping. But now we're going to go through some things where we did some pattern recognition. I think I talked about it in chapter 4. Is probably the biggest reason for using patterns for squaring binomials and stuff like that is to recognize the pattern for factoring purposes. So, and that's what they're going to start with here is recognizing perfect square trinomials. And they go back to what this really means. If I could, I could write this out as this x squared, x plus 5 to the 2 power, the quantity to the 2 power. And they bring out this idea of this pattern that occurs. And hopefully you've practiced this because, I could write this as x plus 5 times the quantity x plus 5, use FOIL, and I'd end up with the correct trinomial. And I wouldn't even think that that's much more difficult to do the multiplication. But if we can see these patterns that occur in factoring, in fact, we'll talk about strategies when we go through that. Like the first thing is always look for common factors, to get the greatest common factor out of every term in my trinomial first. I would say the next thing we're going to look for is this perfect square trinomials. And when you see the patterns that you can look for, the first thing I would look for and second thing and so on. We'll talk about that. So in this, here's the patterns that occur basically if you have a plus b to the 2 power. Really it's the same thing. I don't know if you really need to memorize this pattern because what I do is I get the first term is this squared, the last term is this squared, and then I double this multiplication. I take a times b and double it or take it times 2. Well, the same thing would occur. I really do the same things. I take this first term squared, which is a squared. Negative b squared is a positive b, or negative b to the 2 power is a positive b squared. And then I take a times negative b times 2 and I'll get a negative 2ab. So that's our pattern we went through last chapter. And so we're going to look at expressions. First you need to look at, we can have more complex perfect squares, and that's what they're pointing out here too. Like 4 is 2 squared. We're kind of used to recognizing these types where there's either just a coefficient or the coefficient of the variable is 1. Here the coefficient is 81 and m squared. Well, m squared is a perfect square, and you need to recognize that 81 is 9 times 9 or 9 squared. So this is really 9m parentheses with a to the 2 power, which means 9m times 9m. You got to be careful with order of operations when it comes with exponents too. So this is really 4t, the quantity to the t 2 power. And notice that neither a squared nor b squared is being subtracted. In other words, I would say it this way: there's no way I can get a negative value when I square a term, right? So if this was negative, then basically it doesn't fit my first condition, which is the first term has to be something squared and the second term has to be something squared. And then when that's there, when I do have something squared as the first term in my trinomial and the last term is something squared, then I check to make sure I don't have those subtracted, which I think you've already checked. And then the remaining term needs to, or the middle term basically needs to fit this condition. If I take the terms that I'd have to get the square root of, or what times itself will give me this, and what times itself will give me that, when I multiply those together and double them, do I get that middle term? And you talk about square roots here again, which hopefully you're familiar with, but square root means what number times itself will give me 9 in this case. Okay, so 3 is the square root of 9. Well, let's look at some examples. We can talk about that a lot. I think it really is easier to see as we go through problems. So it says determine whether these are perfect square trinomials. Well, the process we go through again is, well, first of all, I'd say look for common factors and do that first and so on. But in this case, they're just really checking this pattern. So is x squared a perfect square or something squared, and is 9 something squared? Yeah, these two things are, so I've met my first condition. If this was minus 9, that wouldn't be something, right? Like this one right here, I know right away is not a perfect square trinomial because I can't square something and get negative 9. Same here is, you have to be careful though. I'd look at that and go, oh, it can't be. Remember, we probably want to put this in, or we do want to put this in descending order, which would be, here's my degree 2, here's my degree 1. So really this is 16x squared minus 56x plus 49. Now it fits that first condition. This is 4x all to the 2 power, and this is 7 squared. So then I need to go on to the next. This one I can throw out right away because the last term is not something squared. So, and that's what they're going through here. They're going to do A first. It says neither x squared nor 9 is being subtracted. I think that's just a redundant check on whether they're squares, right? And then the remaining term is 6x. Well, if I took the square root of x squared is x, and the square root of 9 is 3. 3 times x is 3x. If I double that, do I get this middle term? And the answer is yes. This is a perfect square trinomial. In other words, based on that, in the process that I go through there, if I was going to factor this, I could say this is really x plus 3, the quantity to the 2 power. And like B is this one right here, that first condition doesn't work, or the first two conditions, right? They say, well, t squared is 9 are squares, and I'd say, well, it's not really. Remember when we were talking about terms, I usually come back to this a lot. Terms are parts of an addition. Even though they write this as a subtraction, this is really, when I say what are the terms of this trinomial, it's t squared, negative 8t, and negative 9. I mean, it's always, the terms are taken out as parts of an addition. That's actually the definition of a term. Okay. So when we go through this, I'd say the first condition didn't work because in B here, right here, I'd say no, negative 9 is not a perfect square. Okay. Now the C, they catch this. They say, hey, you know, it's a B. If you get lazy, you can look at this and say, hey, the last term's negative, but this really isn't the last term if it's in descending order. So make sure you put it in descending order. This is a perfect, or this is something squared, which is 4x, and this is something squared, which would be 7, right? So the next part of that to check is to look at that middle term. So next they note that 16x squared and 49 are squares, right? Neither, they're not being subtracted. In other words, they really are squares. Twice the product of that. If I took 4x and 7 and multiply that, I get 28x. And you double that, you get 56. Now in this case, the remaining term is a negative 56, right? Thus, they can have the opposite product. So in other words, I'm going to end up with, and they're not showing us this next, right? This next part they're showing us. Really, I end up with 4x minus 7 squared. And we'll talk about that. That way the middle term becomes correct, or in the negative. Okay? And that's what they're showing us here. If I have the first and last terms are something squared, and if I can multiply those square roots and double them, and I get this middle term, well, the reality is I could say this b is, in this case, I could say this square root, like that 49, I could say it's negative 7 times negative 7. That's the thing that happens with square roots too, is we have to deal with the fact that, you know, I can multiply the negatives times each other and get my square, right? So again, I think this is redundant. It really is either it's a positive 2 times those product, or a negative 2 times that product, or negative 1 times 2 times that. Okay, so they go through this again. They show that, hey, here's my pattern. When I'm looking at the pattern, it's good to note what the roots are, or basically square roots, because they're going to be the terms in my binomial. In this case, I end up with x plus 3. Notice, and they go through the steps here. Well, this is something squared, this is something squared, that's x and 3. If I took x times 3 and doubled it, I'd get 6x. Hey, this is a perfect squared trinomial. It's going to be x plus 3, the quantity squared. And the reason they know it's not minus 3, because I have to add those together, or multiply them and double it to get this. If I had a negative there, I would take x times negative 3 is a negative 3x times 2 is a negative 6x. So it has to be a positive 3. Okay? Look at B here. Now I have, I check the conditions. First they say put it into descending order by degree of the term. So I end up with t squared minus 14 plus 49. Well, this is something squared. This is a perfect square, or 7 squared. They list it out. I end up, well, I have t and 7. If I multiply those together, which is really, to get a negative, this I have to get a positive times a negative and then double it to get a negative. So I know it must be minus 7. And I can factor that. Now, remember antifoil? You could do antifoil. I would rather recognize this and write out the answer. It is a lot less work to remember these patterns. Now they can be more complex again, where the first term really has a coefficient that's a perfect square, like 100. Here's 81, which is 9 squared. 9 times 10 is 90, right, times x. Double that, you get 180. And one of these has to be negative, because I got a negative 180. So I end up with 10x minus 9, the quantity squared. Here's another one, factor 4p squared minus 12 pt. Now this last example is showing when we have multiple variables. If you think about it, really the pattern's the same thing. Is this something squared? Well, this would be 4p, or excuse me, 4p. It'd be 2p, the quantity squared. Remember, we've got to use our order of operations. It's not 2p to the 2 power. It's the parentheses, because this really means 2p times 2p, which gives me 4p squared. Well, is this something squared? 9t to the 2 power, 9t squared. Yeah, that's 3t to the 2 power here shown. So there's my two terms, basically, of my binomial of 2p and negative 3p. They choose negative because I know it has to be negative in here. And I take 2p times 3p. What do you get? You get 6pt. They usually put it in alphabetical order. And then you double that. Actually, in this case, I get a negative 6pt times 2 is a negative 12. So it's a perfect square trinomial. Here's another one. Again, they like to go through, what do we always do? Always look for common factors first. Then when I have a trinomial, I look for the things that we've covered, which so far are, first I'd look for perfect square trinomials, and then if it's not there, then I look for um, grouping. I think is a very, very good method to practice. You get good at grouping, you're going to save a lot of time, or use anti-FOIL. Okay. And then this last part is another a lot more recognizable thing to do, because we end up with the middle term being 0 times whatever that variables are. And I think I'll stop here and make a second recording again and just go into differences squares.